morning, everybody. There's the usual things. Let's see here. Sure. All right. Especially should I wait just a minute for everyone to get here. There's the attendance and tutoring again. I did have a question for you guys. Has Sanders talked about finding Taylor polynomials the easy way, or is he always doing it by finding all the derivatives and then plugging in whatever the center is? Let me give you an example. No, sorry, something on the floor. Let's talk Taylor polynomials. There's a few that are pretty standard. We'll kind of go over those. The one that comes to mind first, just sure. Okay, you don't think Sean is doing great. Sorry, let me fix my video here. It's showing the wrong way for me. There, that looks better. Let's see, number 3, number 6. Someone asked about 7 and 8 as well. Of course, I accidentally just closed the homework. It doesn't want to come back up. There we go. Yeah, okay, sure. We talked about 6 last week, actually. We did one a lot like it. So I would encourage you to look at last week's. We can do another one similar-ish to it, but that one's kind of special in that. Okay, we also wrote number. Oh, on homework number 6. I see. Yeah. We can definitely talk about one like number 3. Let's talk about Taylor polynomials first, and then we'll come back around to Newton's method. So, Taylor polynomials, right? You're trying to approximate a function using a polynomial, and depending on how good an approximation you want, you can add more and more terms. So, something we could do is say something like, find the. Gosh, I forgot my pens are all terrible. Let's throw these away. Sorry. So find the second degree Taylor series for f of x equal to e to the x squared at x equals 0. And when we say second degree, it just means that the degree should be less than or equal to 2. So if you happen to not get a term where the degree is 2, that's fine. But then you just stop one before that. So let's say, so I need the first derivative and the second derivative to be able to do this. So I need f prime of x. So the derivative e to the x squared is e to the x squared times 2x. I'm also going to get the second derivative, f double prime of x, which is going to require the product rule. That's going to be the derivative of this, which is e to the x squared times 2x, times this still, plus, and then we do the other thing, right? We have this e to the x squared times the derivative of this, which is just 2. So those are the derivatives we need, and then we're going to evaluate them at the center, 0. So f of 0 is looking like e to the 0, which is 1. F prime of 0 is e to the 0 times 2 times 0, which is 0. And f double prime of 0 is, again, a 0 here, but we have a e to the 0 times 2, which is 2. Okay, so then we just have to throw everything into the formula. So this is where you kind of have to remember what the Taylor polynomial is. So Taylor polynomial says that f of x is equal to f of a plus f prime of a over 1 factorial times x minus a to the first. And really this is over 0 factorial if you really want to be extra special about it. Plus f double prime of a over 2 factorial times x minus a squared. And it just goes on. Right? Each next term is the next derivative divided by the next factorial times x minus the center to the next power. How did I get 2 for f double prime of 0? The way I got 2, so when I plugged in 0, right, e to the 0 is 1 times 0 times 0, plus e to the 0 is 1 times 2. That's how I got the 2 there for f double prime of 0. Let's actually go one more term and find the third degree as well. So the third derivative, so this would be really terrible actually. So if I simplify this, this is 4x squared times e to the x squared plus 2 times e to the x squared. And we take the derivative of that, the third derivative, you're going to have to use the product rule here. So I have the derivative of 4x squared, which is 8x times e to the x squared plus 4x squared times the derivative of e to the x squared, which is e to the x squared times 2x. And then the derivative of this is going to be 2 times e to the x squared times 2x. And so if I plug in 0, I'm going to get 0 plus 0 plus 0, right? There's always a multiplication by 0 in this particular expression, so that f triple prime of 0 is 0. Okay, so here's what this is looking like. This is my general formula, and I'm just going to plug in what I know. So I know that f of 0 was 1. We get 1 plus f prime of 0 was 0 over 1 factorial times x minus 0 to the first. And then the second derivative was 2 over 2 factorial times x minus 0 squared. And sometimes it's fine just to leave it like this. Sometimes you should simplify it. Right? This is really 1 plus x, oh sorry, that's 0 times x is 0, plus 2 over 2, right? Because 2 factorial is just 2 times x squared. So the second degree Taylor polynomial, which I think sometimes people write like is t sub 2 of x, is 1 plus x squared. Now, the thing I wanted to point out here is the third degree Taylor polynomial would also be 1 plus x squared, because the third degree term is just 0, right? If we were at the first 4 terms, we'd get, the 1 for the first coefficient, the 0 for the second coefficient, the 2 for the third coefficient, and the 0 for the next coefficient. So it would just be the same as this previous one, plus 0 over 3 factorial times x minus 0 to the third, which wouldn't contribute anything. So the third degree Taylor polynomial would also be 1 plus x squared. And that happens when you have like Taylor polynomials that only have even powers, only have odd powers. Sometimes you'll a certain Taylor polynomial and the next one will end up being the same. Here's the attendance again in case you guys want it. So since he hasn't talked about the short way of doing it, I imagine he probably won't. There are some tricks to these, but they're not that important. So I think, oops, sorry. I think we can just leave that for now. So, one thing here. Let's see. Yeah. All right, let's look at Newton's. So we can come back to Taylor polynomials later if you guys want, but let's look at a Newton's method example. The thing I'll say about Newton's method is it's kind of a pain in the butt, and you kind of just have to use a calculator to do it. But let's look at the example. Let's not do his example because it looks awful. So yeah. So let's say we have, so a way someone might phrase a question like this, kind of the way people start off is, I want to use Newton's method to approximate like the square root of 7. And so the way you do that is you say, oh, I know the square root of 7 is the root or the 0 of the following polynomial, right? The square root of 7 is a solution to x squared minus 7 equal to 0. Or x squared equal to 7. But we usually write it all on one side. Because then what we're going to do is we're going to use Newton's method to approximate the 0 of this function, right? Because here's what this looks like. X squared minus 7 looks something like, I probably isn't the best. The idea is that there's some point there that is the square root of 7, and we're going to use Newton's method to approximate it. Now, the idea behind Newton's method is we're going to make a guess. And really kind of the guess that you start off with, I wouldn't say arbitrary. Usually it's going to be an integer or a fraction that's as close to this number as possible. So if I was to pick between 2 and 3, I'd probably pick 3 because I think square root of 7 is a little bit closer to 3. So I'm going to say my first guess is x naught equal to 3. And now graphically, here's what we're doing. We're going to plug in 3. When you get 3 squared minus 7, which is not 2, 9 minus 7. And then we're going to draw the tangent line there. This is where things are a little bit messy. And that point there, where the tangent line at that point intersects the x-axis, that's our new guess. And then it's just a repetition of this iterative process. So the way we find the next point, there is a formula for it. I kind of know it. I just remember, I don't know if it's a plus or minus, but there is a way of deriving it, right? We're trying to find, so here's what we've got. We've got this point here, which is x naught, comma, f of x naught. And we're trying to find that point there, which is x1, comma, 0, right? It's the next one, x1, and it's where it intersects the x-axis. And so what we're going to do is we're going to say, well, okay, the slope between these 2 points, which I can find using the slope equation. So it's the difference in the y's, f of x0 minus 0, over the difference in the x's, which is x0 minus x1, is equal to the slope of the tangent line. But the slope of the tangent line is the derivative at the point x naught. And then we're going to use this to solve for x1 because we're trying to input x naught to get to the next value, which is x1. So I'm going to multiply both sides by this. I think some people do some other thing with it, flip, whatever. I'm just going to do it the way that makes sense to me. So I'm going to say f of x naught equals f prime of x naught times x naught minus x1 divided by this. X naught divided by f prime of x naught equals x naught minus x1. Add this over here, subtract this over there. So I'm adding x1, and I'm subtracting this, and getting x naught minus f of x naught over f prime of x naught. So that's always how you get the next value. You take your previous value, so 3 in this case, and you say, okay, it's going to be 3 minus the function evaluated at 3 over the derivative evaluated at 3. And then you just keep repeating that process. So the dumb thing about Newton's method is it's just kind of like you're just plugging into this formula over and over and over again. The hard part about it is the numbers usually eventually start to get kind of terrible. So let's see here. So my function was x squared minus 7. My derivative of that is 2x. My x naught was 3. And then my formula is, so the actual formula isn't x1 equals there, it's x sub n plus 1. The next value in the sequence, the iterative sequence, the recursive sequence, is x sub n minus f of x sub n over f prime of x sub n. Which you could totally write out the formula for, right? You could say it's going to be, you know, x minus x of n, really. F of x of n is x of n squared minus 7 over f prime of x of n is 2 times x of n. So then we're just going to start with x of 0 equal to 3. So then x sub 1 is going to be x sub 0 minus x sub 0 squared minus 7 over 2 times x sub 0. And let's see what we get. We get 3 minus 9 minus 7 is 2 over 6. We get 3 minus 1/3, which is 8/3, or 2.6666666. Now here's the things start to get done. To find the next one, you have to plug in the new one. Right, so I'm going to take my x sub 1 and plug it back into this iterative formula to get x sub 2. So x sub 2 is going to be x sub 1, which is 8/3 minus 8/3 squared minus 7 over 2 times 8/3. And here's where things start to get messy. Yeah, it's kind of a pain. This is where I would probably get out a calculator. 8/3 squared minus 7 divided by 2 times 8/3, which is 16/3, or times 3/16. And then 8/3 minus that. I got 2.6458. And then you have to do that again, right? So then you plug that number back into this formula to get the third. So the thing I feel like is kind of silly about this is you keep plugging in the same number or plugging things in the same pattern, but you have to use a calculator. Like, I mean, you could do it by hand. You do the fractions. Like it's be 64/9 minus 63/9 over 16. But like, you're just supposed to use a calculator. And there's actually one thing that's kind of nice to do, which I'll show you guys in a second. Yeah. So I'm gonna do one more. So I'm just gonna take this 2.6454 and plug it into this saying. So I'm gonna say my next thing is I'm gonna do second answer minus parentheses my answer squared minus 7 divided by 2 times my answer. So second answer squared minus 7 divided by 2 times my answer. Which is easier with different calculators depending on, let's see what we get. So this time I got almost the same number. I got 2.64575. I mean, almost the same up to a certain decimal. And if you did it again, you probably get something even closer to the square root of 7, which the square root of 7 is, sorry, just 1 second. The square root of 7 is about, so it's, we are right to the decimals, right? It's pretty cool. So on my calculator, the last one we did, the third one, we got 2.645751312. And the square root of 7 is approximately 2.645751311. So with 3 iterations, we have a really good approximation of the square root of 7. So that's kind of the idea. It's just that the calculating of it is kind of a giant pain in the butt. So let's look at one more example. Let's look at an example more similar to what he's done, although really it's the same idea. And I want to look at something. I want to make it something that actually has a 0 because there are. Oh, if it's a cubic, it always has a 0. So let's just do a cubic, right? Because that's what he did. Yeah. Let's say our function is 2x cubed plus x. Let me be careful not to pick something that actually has a nice 0. Minus 1. That seems probable. Yeah. probably looks something like, if I plug in 0, I get -1. If I plug in 1, I get 2 plus 1. Ooh, I have to be careful here. So there's definitely a 0 there. There might be one somewhere else. I wouldn't round. So Shayla, so someone asked, sorry, no, it's fine. Someone asked about rounding. I typically try not to round until the very end. So like I would just use the value from the calculator in the next problem. So actually let me address that with this next example. The problem, so I'm just worried that there could be an issue with this example because of how cubic functions sometimes work. Let me think for 1 second. Let me graph it in Desmos because that's actually what I'm going to do with you guys anyway. So let's go over to Desmos here for 1 second. I don't know if my homework went well. Sorry, I might have picked up the wrong graph. 1 second. Sorry. So I'm going to look at this, and I guess I can share my screen with you guys because you can want to see the graph too, maybe. Here's the graph of the thing I just made up, which is 2x cubed plus x plus 1. Yeah. So this graph isn't a good example for this process. So let me tell you why. So let's say we started with a guess of, oh, I did a -1. Sorry, it's still not a good example. Okay. So the reason this isn't good is because, so let's say we see that the 0 or the root of the graph is right here, or a little bit bigger than 1, right? Like it's about, I don't know, oh, sorry, it's a little bigger than 1. It's like 0.59. So I'd probably guess like, I don't know, zoom in a little bit here. I'd probably start with a guess of 1/2. And here's the problem with this particular type of function. If I guess 1/2, I'm going to end up on the function right here. And then if I draw the tangent line, look what the tangent line is going to do. The tangent line is going to shoot me way out that way. In fact, the tangent line looks like it doesn't even hit the function until we get way down here. And we could find the equation of the tangent line if we wanted to. It's probably something like, I should be able to figure this out, but with more. 6x squared. Anyway, the point is that, sure, we can draw it like this. Y equals, I think it's a little bit bigger than that. Sorry, guys, 1 second. Sure. I'm just trying to like guess as to where it lies. That's a little bit down. Sure, the tangent line's about there, right? Maybe not exactly. It didn't get exactly right. But let's pretend like the tangent line's hitting here. And the problem is then it's going to take us all the way over to this point here. And that's an issue because it's, oh, sorry, I'm getting this backwards. It's taking us further away. And we actually end up over here. And then we go up here and it, maybe this one, sorry. Sometimes this stuff gets me kind of thrown, I won't lie. This one looked like it might be an issue, maybe it's not. So let's actually go attack it and see what happens. Sorry guys, I thought I was seeing something else. Sometimes these third-degree polynomials, they kind of circulate in this never-ending pattern. Let's find out. So I looked at the graph and I saw that I was going to guess x equal to 1/2. X not equal 1/2. And we know we need to use our usual pattern. So remembering the pattern the right way is always a problem for me. It's x sub n plus 1. It's x sub n minus the function divided by the derivative. Okay, so I'm going to plug in 1/2. And it's going to get a little bit messy. So this is definitely where I'm going to do something that I think is kind of smart. This is where I wish I had my graphing calculator, and I do not. Here's one way you can do this. I mean, you can plug it into a computer, which you can actually do with Desmos or something else. Let's see, let me share my screen again. So I was thinking of doing this in a graphing calculator, is you can actually graph the thing that you're trying to calculate. So if I graph, let's see, so I'm going to graph y equal to x minus f of x, which is just that function. So 2x cubed minus x, sorry, plus x divided by the derivative, which is 6x squared plus 1. Okay, end those parentheses. And so the nice thing about this is it doesn't really tell us anything graphically, but it tells me that if I plug in 1/2 for x, well, I can go over here and actually, you know, I feel like there's got to be a way to evaluate this. Oh, there is. There's like a table thing you can do. Yeah. Cool. So if I plug in 1/2 or 0.5, I want y1 to equal this function up here. I'm going to call this y1. I'm smart. Darn it. I know I did this before, and there's like too many variables. Trying to find the x. Let me just call this x. Yeah, I did it. I should just call this y. Okay, but I see a problem, and this is the problem I think that you were kind of talking about, person. What's the problem? I just table headers fine. I guess it was working fine when it was over here. So yeah, I want more decimals here. That's about. So the idea I was trying to think of is you could do this and say, okay, like I'm going to plug this in to get my y1. Right, this is giving me the value when I plug in 0.5 for x. So I'm getting, right, if I actually plug in 0.5 for x, I'd be getting so if I plug in 0.5, I'm going to get x1 equal to 0.5 minus 2 times 0.5 cubed plus 0.5 minus 1 all over 6 times 0.5 squared plus 1. And that should end up being about 0.6. But again, I feel I agree with your sentiment is that the decimal points, right, it's a pain, right? So if I do this, I'm going to get, let's see, 0.5 minus, and this is where you kind of have to use the calculator. So when I do this, I am getting, so 2 times 0.5 cubed. Sorry, the whole thing. I said 0.5 minus 2 times 0.5 cubed. Yeah, it's plus 0.5 minus 1 divided by 6 times 0.5 squared. So that's, right, 3/6 we have plus 1, which is exactly 0.6. So I was worried that what they were giving me there wasn't actually the value, but it is. So that what you can do then, sorry, going back to this, is then you can plug in the y value here to get the next x value. So if I plug in 0.6, okay, it gives me the next one, which is 0.5899. And then unfortunately, I don't think there's a way, can I copy that? No, I just pasted the zoom attendance in there. So you can kind of use this. It'd be cool if you could copy that, but you can't. So yeah, I guess I could start just typing that in 0.58987342. And that gives you the next value, which is really, really close. So this one, yeah, so I've got, so this is my x0, this is my x1, this is my x2, and then plugging in, I guess this is my x3 right here. So that would be the third one, and that's where I would cut it off at 4 decimal places. So I would say that my answer to this question, right, what's the root of this polynomial, I would say it's approximately 0.5898, because I would round that 7 up to an 8 because of the 5 after it. So the pattern isn't too terrible, but you just keep plugging the same thing back into the same formula. It's the using the calculator and making sure you're careful with the decimals that's kind of the awful part. Well, so here's the thing. I mean, yes, but so the actual root here, right? If we go back to the original function, which I guess I lost, I guess I did an original function, is that you can see what the root is, right? So if I add a function here, sorry, maybe you could add a function. There we go. Right. If I go back to the original function, the problem is that, right, this will tell you what the root is, or approximately what the root is, right, which is right there. So it's about, right, but it's only telling us about 0.59. So it's not like it's super duper helpful. It's like, yeah, sure, the answer, the number we're getting closer and closer to looks like it is that number, but I don't think that's an exact number, right? I think that's an approximation. So yes, but not really. Let's see, there was something else. Oh yeah, I know, someone. Yeah. So what I would say about Newton's method is you just kind of have to memorize, or maybe not even memorize, but you have to remember the formula, and you just have to keep plugging things in over and over and over again. Usually, for Newton's method, they will just tell you how many times you have to do it. Right? In the homework problem he gave you guys, he said you had to find x sub 3. So that means you have to do it 3 times. Right? You start with x sub 0, you do it once to get x1, twice to get x2, a third time to get x3. Yeah, they could ask it on a test, and they could, but usually they only ask you to do it like, usually on the test, if someone asks you to do a problem like this, it's usually designed so the numbers aren't terrible until maybe the last step. Like you plug in x sub 0 to x sub 1, and you get like a nice-ish number. And you plug in the x sub 2, and it's still like not terrible. And then when you plug in x sub 3, the numbers start to get awful, but that's usually the last one. And so it's like, okay, you got this thing at the end that wasn't super nice, but the ones before that weren't so bad. I don't have an example, but off the top of my head. I know where one is, kind of. I know where to look for one later. So that's what I would say about that is, yeah, so someone could ask, for example, I mean, let's see. So let's say someone said, let me think for 1 second here. I want to find the, so estimate the root of, let me think for 1 second here. Sure. 2x squared minus 2x minus 3. Starting with x equal to 2. This one might be dumb, but we'll do it anyway. X of 0 equal to 2. So again, I'm just using my formula, right? My formula is x of n plus 1 is x of n minus f of x of n over f prime of x of n. And so plugging into, well, I need to write my different, my words. I need to write my function, 2x squared minus 2x minus 3, and my derivative. Well, that's going to be interesting. Huh. So this is actually not a good example, but I'm going to show you why. So let's see what happens when I do this. If I plug it in here, if I plug in 2, I get 2 minus f of 2 is, what did I do? I think I did something crazy here. What's going on? Huh. Well, anyway, we'll see. So plugging in 2, I get f of 2, which is 2 times 4, 8 minus 4, which is 4 minus 2, which is 1 over, oh no, I'm just doing bad math in my head. So here's the first step, and I get 2 minus 1/8, which is either 15/8 if you prefer, or I think that's 1 point something, 1.875. And then we would plug that into the next one. So maybe here it would be reasonable to ask, like, find x sub 2. Because if you find the next one, it's still not too terrible to plug in 15/8, right? You're going to get 15/8 minus, okay, 2. Okay, maybe it's a little terrible. What I'm saying is kind of whatever, like if you were asked to do one on a test, this would be like the last step. You'd be like, oh, I got the last one, and it looks like this awful thing. And maybe you would need to simplify it, but probably not. Here's the link to the, to the attendance and the tutoring. All right, so let's move on and talk about absolute extrema. We definitely talked about last time. And again, it really has to do with finding the critical values. So let's see, where do I want to go with this? Let's say we have a function f of x equal to x squared over x minus 1. Now I want to find the critical values. So I take the derivative. I'm going to see where it's 0 or undefined. Take the bottom times the derivative of the top, which is 2x, minus the top, x squared, times the derivative of the bottom, which is 1, all over the bottom squared. So I end up with, let's see, so distributing here, I get a 2x squared minus 2x minus an x squared all over x minus 1 squared. Simplifying the top, a 2x squared minus an x squared is just an x squared. So x squared minus 2x over x minus 1 squared. And then finally, factoring the top, I'm going to get x times x minus 2 over x minus 1 squared. And I want to know where that's equal to 0 or where it's undefined. So let me ask you guys, for 0, what values of x make this thing equal to 0? Yep, 2 and 0. Now, here's something else we need to say, and this is kind of a tricky point. X equal to 1 does make the derivative undefined here. But x equal to 1 is not technically a critical value because it's not in the domain of the original function. So x equal to 1 is not a critical value. Even though it makes the derivative undefined, it's not, right? It's actually where we have a vertical asymptote. So it's not really a place where you could have a maximum or a minimum. Now, later on when we start graphing functions and using the derivative, it's still helpful to know that the derivative is undefined here because it might change signs. But as far as the technical definition of what a critical value is, x equal to 1 would not be considered a critical value. So then I could ask a question. Well, how about like this? So what is the absolute maximum and minimum of this function on the interval from 1.5 to 4? Well, just like any time when you're doing the absolute max and absolute minimum, or the global max and global minimum of a function on an interval, you have to plug in the critical points and see what the function is doing, and then you have to plug in the endpoints. Now, one thing to be aware of here is that we don't need to use both critical points because x equals to 0 is not in the interval. So we don't need to know what f of 0 is. It doesn't tell us anything. What we really need for this one is f of 1.5, or I'm going to write that as 3 halves. I need to know f of 4, and I need to know f of 2. But f of 0 isn't helpful here. So f of 2 is going to be 2 squared over 2 minus 1, which is 4 over 1. F of 4 is going to be 4 squared over 4 minus 1, which is 16 over 3, which is 5.33 continuous. F of 3 halves is going to be 3 halves squared divided by 3 halves minus 1, which is 9/4 over 3 halves minus 1 is 1 half. That's 9/4 times 2 over 1, which is 9 over 2, which is 4.5. So looking at all these numbers, I see that 4 is the smallest. I see that 5.33 forever is the biggest. I just picked 3 halves. So because it's the end point of my interval, right? 1.5 is 3 halves. I was just using a fraction because it's easier for me to square 3 halves and get 9/4 than it is to square 1.5 and get some other decimal. So here, and again, the language is important. I would say I have a minimum value of 4. I would say the minimum occurs at x equal to 2. I have a maximum value of 16/3. The maximum value occurs at x equal to 4. Other questions about this one? A slightly different problem. Sure. Let's look at sorry, 1 sec. X to the 2/3. Sure. So let's look at this function, f of x equal to x to the 4/3 minus 4 times x to the 1/3 on the interval from -1 to 8. So someone asked a good question privately. When we get the minimum and the maximum values, they have to be between the number in the brackets. Yes, and I thought we have to use brackets. So here's what we did, right? So we found the critical values independent of the interval, right? We just said we take the derivative, set it equal to 0, and undefined. I get 0 and 2. I don't get 1 because it's not in the domain of the function. Then we said, okay, well, for my critical values, only this one is between 1.5 and 4, right? 0 is not, so it's out of the question. And then we take the endpoints, right, which are 1.5 and 4, and plug them in and see what the function's equal to. We also plug in the critical values that are between the endpoints to see what the y value is. And then we just look and see which one's the biggest. Oh, this one's the biggest. Which one's the smallest? Oh, that one's the smallest. So that's how we identify what the critical values are, or what the global maximum and global minimum are. So let's look at this next one, which is a little bit tricky, but it's fine. So let's find the critical values. So I'm going to take my derivative, which is going to be, so I'm going to use the power rule. It's 4/3 times x to the 1/3 minus 4 times 1/3 times x to the -2/3. And so before I can solve this, I really need to factor. So I've got 4/3 times x to the 1/3 minus 4 times 1/3 is 4/3 times x to the negative 2/3. I'm definitely going to factor out a 4/3. I'm also going to factor out x to a power. What power of x should I factor out? Yeah, yes, Jenny. When we look for the critical values without the interval first. So if I was factoring out, I could factor out x to the what? So 1/3 is the guess I often make at first, but here's the thing. So let me actually show you a different example just to kind of point out. If I was factoring x to the 5th minus x to the 2nd equal to 0, I would definitely factor out an x squared because that's the smaller power. And we left with an x cubed minus 1. 0. I could also factor out the x to the 5th, but things are weirder. If I do it this way, if I factor out an x to the 5th, I'm left with a 1 minus 2 minus 5 is negative 3. Which would still work, but it's just not what I want. So the thing is here, I actually want to factor out the smaller power. And that's always the case, right? We always want to factor out the smaller power so that the bigger power still has some of the variable left. So we do want the negative 2/3 power to be factored out because it's the smaller power. The negative number is always smaller than the positive number. So I've got 4/3 times x to the negative 2/3. And then I'm left with, well, I can't factor out the 4/3, so it's still 1. And then x to the 1/3 minus, or sorry, divided by x to the negative 2/3. I'm dividing out the negative x to the negative 2/3. And when I divide these two things, I subtract the powers. And 1/3 minus negative 2/3 is 3/3, or 1. Minus here, I'm just left with a 1. So I factor out the 4/3, I factor out the x to the negative 2/3. Okay, so here's what I've got. And I'm going to rewrite this. I've got 4 over 3 times x to the positive 2/3 times x minus 1. All right, what's a critical value of this? What's going to make this equal to 0? So those are both critical values, but only one of them makes it 0. So if I plug in 1 minus 1 is 0. If I plug in 0, 4 divided by 0 is going to give me undefined. Now, I do want to be super, super clear. In this example, 0 is a critical value. Because in this example, 0 is in the domain of the original function. I look back at the original function, I can plug in 0. 0 to a positive power is just 0. Minus 0 to a positive power is still just 0. So here, 0 is a critical value. It's a real, I usually call these other ones, I call this number here, I usually call that a pseudo critical value because it's not really a critical value, but we still use it like it is. Whereas here, x equal to 0 is a genuine critical value. So then, we're just going to evaluate this function. And all 4 of the, oh, well, actually, we should check. So are my critical values in my interval? Yes, they are. Both 1 and 0 are between -1 and 8. So we're going to test all 4 points. f of -1, f of 8, f of 0, and f of 1. Some of these should be easy. F of 1, 1 to any power is 1. So I get 1 minus 4 times 1. F of 0 should also be easy because 0 to any positive power is 0. So I get 0 minus 4 times 0. Let's hold off on f of 8 for a second. F of -1 should be fairly not too terrible because -1 to the power is either 1 or -1. So -1 to the 4th power is positive 1, and then the cube root of 1 is 1. Or you could say -1 to the 1/3 power, or the third root of -1 is -1, and then -1 to the 4th is possible. Minus 4 times, all right, what's the cube root of -1, or what's -1 to the 1/3 power? It's -1. right? -1 times -1 times -1 is -1. So the cube root of -1 is -1. And then, so that's going to be 1 plus 4, which is 5. And then 8's going to be the tricky one. 8 to the 4/3 is 16. Because it's the cube root of 8, which is 2, and then that number to the 4th, which is 16. Minus 4 times the cube root of 8 is 2. 16 minus 8 is 8. Okay, so here's the biggest number. Here's the smallest number. So I would say I have a maximum value of 8 that occurs at x equal to 8. I have a minimum value of -3 that occurs at x equal to 1. All right. A couple people requested I do some Taylor polynomial videos, so I will definitely do those this afternoon and post them up. I'll try to do some examples that are fairly straightforward. And that's all I've got for today. Do make sure you fill out the attendance form, and I will see you guys on Wednesday. Take care. You're all very welcome.